Imagine a computer that could solve incredibly complex problems, ones too difficult for even the world's most powerful supercomputers to handle in a reasonable time. That's the exciting promise of quantum computing, a revolutionary technology that harnesses the strange principles of quantum mechanics to perform calculations in a way that's fundamentally different from traditional classical computers. This amazing technology holds immense potential to completely transform key fields such as medicine through faster drug discovery, materials science for new inventions, and artificial intelligence for smarter systems. If you're excited to dive into this groundbreaking technology and learn more about the quantum world, make sure to hit that like button right now and subscribe for even more fascinating insights. Our journey into this fascinating history begins back in 1900 with the physicist Max Planck, who revolutionized the field of physics through his pioneering studies on black body radiation. In a bold move, Planck proposed that energy is not continuous but is instead emitted and absorbed in tiny, discrete packets, which he named quanta, thereby marking the official birth of quantum theory. Just 5 years later, in 1905, the brilliant Albert Einstein built directly upon Planck's foundation by providing a groundbreaking explanation for the photoelectric effect. Einstein boldly proposed that light itself travels in discrete packets known as photons, which further solidified and expanded the revolutionary concept of quantization in physics. Fast forward to 1913, when Niels Bohr introduced his groundbreaking model of the atom, skillfully incorporating these emerging quantum ideas into atomic structure. Bohr's innovative model clearly explained that electrons orbiting the nucleus can only exist in specific, quantized energy levels, like steps on a ladder, rather than anywhere in between. The quantum revolution gained more momentum with Louis de Broglie's bold hypothesis about matter waves, suggesting that even particles like electrons possess wave-like properties as well. Then in 1925, Werner Heisenberg developed matrix mechanics, one of the very first mathematical formalisms that successfully described the behavior of quantum mechanics. Erwin Schrödinger followed closely in 1926 with his elegant wave mechanics approach and the famous Schrödinger equation, which remains a fundamental tool for accurately describing quantum systems today. The next year, in 1927, Heisenberg introduced his famous uncertainty principle, profoundly stating that it's impossible to simultaneously know both a particle's exact position and its momentum with perfect precision. Paul Dirac took quantum mechanics to new heights by unifying it with special relativity, resulting in the powerful Dirac equation that predicted phenomena like antimatter. The theoretical foundations for quantum computing truly began to take shape in 1980, thanks to Paul Benioff's innovative work on quantum mechanical models of Turing machines. Benioff's pioneering efforts laid the crucial groundwork needed for scientists to understand exactly how quantum principles could be practically applied to computation. In the early 1980s, the legendary physicist Richard Feynman famously proposed that quantum computers could efficiently simulate other quantum systems that classical computers struggle with. Feynman astutely highlighted the inherent limitations of classical computers when it comes to accurately simulating the complex and intricate phenomena of the quantum world. Then in 1985, David Deutsch introduced the groundbreaking concept of a universal quantum computer capable of tackling any computation. Deutsch explained in detail how quantum logic gates operating on qubits could enable true general-purpose quantum computation, thereby opening up vast new possibilities for the field. A major breakthrough arrived in 1994 with Peter Shor's revolutionary algorithm designed specifically for factoring very large numbers exponentially faster than classical methods. Shor's algorithm dramatically demonstrated the enormous potential for quantum computers to significantly disrupt and transform the world of cryptography. 2 years later, in 1996, Love Grover developed his innovative search algorithm, which provides a valuable quadratic speedup for efficiently searching through massive, unsorted databases. Soon after, early experimental implementations began to emerge, including IBM and Stanford successfully factoring the number 15 on quantum hardware, and later, Google boldly claiming to achieve quantum supremacy. Looking ahead, by 2026, we anticipate a significant and exciting shift from purely experimental quantum computing efforts to the dawn of commercially viable real-world applications. Major breakthroughs are expected particularly in quantum chemistry for accelerating new materials design and revolutionary drug discovery, as well as advancements in materials science overall. Quantum hardware and software will experience major advancements, including better support for more reliable and fault-tolerant computation using techniques like integrated photonics. We'll also witness an increasing and powerful integration of artificial intelligence with quantum technologies, paving the way for highly effective hybrid solutions across industries. Cloud platforms will make quantum as a service, or QaaS, far more accessible and user-friendly, allowing a wider range of developers and industries to harness quantum power easily. Looking specifically ahead to 2026, there will be a strong and growing focus on improving reliability through advanced error correction techniques in quantum systems. Hybrid quantum classical workflows will become far more common and practical, smartly leveraging the unique strengths of both computing paradigms for optimal results. Innovative new materials and sophisticated processing techniques will continue to dramatically push the boundaries of what's physically possible in next-generation quantum hardware. The transformative potential of quantum computing to revolutionize countless industries, from healthcare to finance, is truly immense and only continues to expand rapidly. Indeed, the quantum revolution is really just beginning, and the bright future ahead promises even more astonishing discoveries, innovations, and practical applications beyond our imagination. Stay tuned and keep watching for more exciting updates on this dynamic, rapidly evolving, and incredibly promising field of quantum technology.